Outside. Okay. Do I have to rap on the tables? Yeah. This is the English system, right? Yeah, very good. All right. So it's my pleasure today to introduce Benjamin Andrews, who's coming up to us from the Smithsonian Institution to talk to about some of his research looking at basically pyroclastic density flows. There's going to be some great movies, I think, right? Yeah. Ben's been working in the global volcanism program, and so if you're interested in volcanology, I know there's a few of you in this room, you should definitely go down and visit them and see this setup. It's pretty cool. I went down and saw it like a year or two ago. It's pretty impressive. So I'll give Ben the full time, so let's give him a warm welcome and take it away.
Thank you very much, and I'm very happy to be up here today. I've had some great talks with people throughout the day, and it's really ridiculous that those of us from Smithsonian don't, get on that onerous 20-minute metro ride to come up here more often, because we really are quite close. So like Nick said, I'll be talking today about research that I've been doing with various colleagues at Smithsonian for almost 5 years now, where we can study and essentially we can study pyroclastic flows or pyroclastic density currents in the laboratory using scaled experiments. And that's what we see here. This picture right here, this yellow stuff, this is not a computer model. This is those are real experimental data. We're looking at a three-dimensional reconstruction of a current as it was moving. The only thing that's faked in this picture is the base, which is we made that white and then added those nice little half-meter ridges so we could have some reference frame. So before I get into the science, I should really thank the people and agencies that have made all this possible. So of course I work at Smithsonian, and Smithsonian generously pays my salary and provides me a space and a home, and NSF is funded this work, but probably more importantly than the agencies are the people that allow me to do my work. So Rob Denon helped me build the tank that I'll be showing you, and Tim Gooding and Tim Rose helped make many of the instruments that are in it and helped me get this thing going. Mary Benage is a postdoc now at the USGS, and she helped with thinking about a lot of the experiments to run and how to make things work. And then graduate students Kristen Foria and Sean O'Donnell helped run experiments, and so did Emmy Davis. Now, I've also been fortunate to have several undergraduate interns, including Gabby Ramirez and Brianna Marshall and Darian Flores, who actually I think are all off to graduate school now, which is fantastic. And a lot of the data I'll be showing today was data that they helped collect. And finally, two high school students, Grace Cooper and Josh McCoy, and Josh's father, Tim McCoy, who some people know here, came and ran experiments, and I really should find out what award we won, but I believe with the experiments they ran in my lab, they won 2 science fairs. So that might be better than anything else. We got the blue ribbon at a science fair, twice. So
one of those science fairs, Tim was a judge?
He was not a judge. That's a fair question. Tim was not a judge. All right, so what are pyroclastic density currents? Well, this is a picture of one right here happening at Mayon Volcano in the Philippines. And just so you know, as of just a couple weeks ago, Mayon was still erupting, not quite like this. It's erupting lava rather than pyroclastic flows, but it's a very active volcano. We have this nice, in the background, we can see the shape of this volcano, a great big perfect cone. And coming out of this cone are these clouds of ash and gas and pumice. And some of that rises up into the air to make a buoyant plume, but a lot of it is flowing down the sides as pyroclastic flows. And in fact, these guys here are also giving rise to material which then lifts off to form a buoyant plume. So pyroclastic flows are these really scary currents of hot ash and gas and rock. And we care about these because they're highly destructive. They can destroy pretty much anything in their path. We have up here in the upper left a picture from the aftermath of the El Chichon eruption in Chiapas, Mexico in 1982. And in the background, you can see various trees, the jungle forest that's been leveled. But in the foreground, this is all that remains of a building. This is a piece of a wall. There's a hammer handle right there for scale. And this is rebar right here. So we can see that this pyroclastic flow came through from the right to the left, knocked everything down, destroyed it, bent this wall. It caused a big problem. We see a similar photo down here from a much smaller eruption at Montserrat, where we can see a pyroclastic flows come through from right to the left. And all that remains of this structure is the concrete slab that this fellow's standing on. And again, bits and pieces of the wall, and again with the rebar sort of indicating the relative flow direction, or in the background, this fence line. So we can see this is a very destructive current went through, a very destructive mass flow. It destroyed almost everything in its path. It also really didn't leave much of a deposit. Right where he's standing, there's maybe, I don't know, a centimeter or something of ash between his feet and the original concrete floor. So it's highly destructive, but it might not necessarily leave behind much of a deposit. And finally, this picture here is a pretty amazing photo from the aftermath of the 1902 Montpellier eruption. And we're looking at the interior of a ship that was in the harbor and was set on fire by the pyroclastic flows. So all these, you can see the anchors up here, and all these little pokey things coming out the side, those are nails that originally would have had wood coming all the way to the edge. But when you set the ship on fire and it burns from the inside out, you're left with essentially a forest of nails poking inward. So these are highly destructive, terrifying currents. And so we want to know more about them because they affect the world in a geologic standpoint. They also can pose significant hazards to humans. So for our outline today, we'll talk a little bit more about what are pyroclastic density currents, then talk about experimental methods, and finally, after that, we'll go into results and basic behavior, sort of how far do pyroclastic flows go, what directions might they go, and then we'll get into some more quantitative understanding of air entrainment in pyroclastic density currents. All right, so pyroclastic density currents, the name pretty much says it all. We could also refer to these as pyroclastic flows or pyroclastic surges. Pyroclastic density current, or PDC, is really a catch-all term. And actually, I should say right here, if anyone has any questions, please feel free to shout them out and ask at any time. So a pyroclastic density current is a gravity flow, a gravity current, which is made up of pyroclastic material, so pumice and ash and rock that have recently been erupted from the volcano. And it's traveling because it's denser than the ambient atmosphere. So if we think about a pyroclastic flow, it's a turbulent, the upper part of it is a turbulent mixture of ash and gas and rock. And somewhere down near the base, we also have particles that are sedimenting out. And as this current moves, because it's denser than the atmosphere, we can calculate its speed and predict its speed based upon the density of the current, the thickness of the current. We can do all of this based on some amazing laboratory work that's been performed over many decades. And a lot of that work has been done on powder snow avalanches and turbidity currents. But what sets pyroclastic flows apart from these other ones is that pyroclastic density currents, pyroclastic density currents are hot. And that means that whereas a normal density current can change its density by either sedimenting particles out of the bottom or mixing air in at the top and at the front of the current, a pyroclastic flow, because it's hot, when it mixes air in, it will then expand that air, and that'll cause a further reduction in density. And so this means that we should expect that pyroclastic density currents might actually behave differently than do other density currents, such as powder snow avalanches or turbidity currents. And we see a picture of that right here from Redoubt Volcano erupting in 1989 in Alaska. Now, the title up there is pretty important. Pyroclastic density currents are very common in explosive volcanic eruptions. Sinabung Volcano is a volcano in Indonesia, and it was erupting, it's still erupting right now, and there was a period a few years ago where, as this lava dome was erupting, it was generating up to 40 or so pyroclastic flows each day. And it was for quite a while. So it was just boom, one after another, lots of pyroclastic flows coming. And we see one of those, this is again Redoubt in Alaska, but we see a pyroclastic flow similar to what Sinabung made. So this is the mountain right here, Redoubt Volcano. And if you look, there's this beautiful buoyant plume, but it's not coming out of the summit of the volcano. Instead, it's coming off of the flank. And this plume is rising because a pyroclastic flow went down the Drift River Valley. And as that plume moved, it mixed in air until it became less dense than the atmosphere, and then lifted off to form a buoyant plume that rose up to, well, if we eyeball it here, this is about a 10,000 foot mountain. So this plume is up at approximately 30,000 feet. What flies around at 30,000 feet? airplanes. So I don't know if it was this eruption from Redoubt, but in this, or this particular plume from Redoubt, but in this eruption cycle from Redoubt, a 747 passenger jet was very nearly shot down by exactly this type of eruption. And you might remember from, I guess, wow, it's getting many years ago now, almost 7 years ago when Eyjafjallajökull erupted in Iceland, a very small eruption that happened to put a lot of ash in exactly the wrong place, and it shut down air traffic over all of Europe for about 2 weeks. And I forget how many flights were shut down. It was like, I don't know, 10,000 flights or some ridiculous high number of flights were shut down. No airplanes were traveling, no people were hurt, which is good. But again, we see that pyroclastic or ash from these eruptions can cause a big problem. All right, now I was talking with, I think with Ved about this earlier, that Ved asked me, well, how do you study pyroclastic flows? And we could study them in nature, but that's kind of a bit of a problem. As Ved was saying, these things are dangerous. This is a picture here from August 7, 1980 at Mount St Helens, and we can see a pyroclastic flow that's coming down the north slope of the volcano right here. And you really would not want to be in front of that because, well, it would clobber you, is I guess the simple answer. But these are hard to study because they're very dangerous and you don't know exactly when they're going to happen. And you also don't know exactly where they're going to happen or where they're going to travel. So they're not very predictable. They move at very high speed. This might be a little on the higher end for the velocities, but a typical pyroclastic flow might be moving at 30 meters per second. Some of them have even gone faster than 100 meters per second. So this is not a terribly bad estimate, but these are moving very fast. They're not constrained to low topography. They can go pretty much anywhere they want within reason. They're very hot. The currents coming out from St Helens in this picture, this is probably about 400 or 500 degrees C. There's other pyroclastic flows sometimes could be 800 or 900 degrees C. So depending on the magmatic temperature and how much air it's entraining and where we look at it. Now, one of the things that makes these hard to study in nature is that we can't see their internal structure. When we look at a picture like this of St Helens, or of this eruption column, we see these beautiful sort of coliform turbulent structures on the outside, which is telling us a great deal of information about how the current is interacting with the air, but we can't see anything that's inside of that plume. I can make a guess as to what the internal velocity structure looks like, but it's purely a guess. I don't know anything about, from a picture like this, I have no direct observation of what's actually happening at the base. I can make some great guesses, but it would really be a guess if we only had this picture. And so along with that, we see that these pyroclastic, or natural pyroclastic flow essentially has an unknown grain size distribution. We know it has some fine ash, we know it has some big rocks, but we don't know what the exact mixture is ahead of time. We don't know what the density is like. We also don't know what the density is like or how that density varies through space and time, and that's ultimately going to determine how far this current might go. We don't really know the temperature ahead of time, and we don't know if we were to point an infrared camera at this pyroclastic flow, we would get some amazing, really cool looking pictures, but they'd be, again, just telling us what the skin is like. They'd be telling us what the outer, I don't know, half meter or meter of that cloud is like, not what the interior is. And we have no real idea of what the velocity distributions are like in there from a natural current. So another way we could study these is to look at the deposits. So this is a picture here of, this is Jürgen Kienle hanging out at Mount Augustine in Alaska, and he's picking up some great big, I think it's a big pumice, or else he was really strong. And he might have been really strong. So this is from a small volume pyroclastic flow at Augustine. And this is clearly the current moved those rocks. Those rocks were not there before the eruption, but also that's only telling us some component of what was in the current. The whole current wasn't only made of rocks this big. We know there was lots of fine ash. Where did that go? So we can also look at some place, we can see an example of this at like St Helens, where this is some work that Brittany Brand and Nick Pollock have been doing for quite a few years now, looking at the internal structure of the deposits from May 18th at St Helens. And up above we have, this is, well, there's a scale bar, so 8 meters. Our cliff here is maybe 20 meters tall, something like that. And this was all deposited on the afternoon of May 18th, some between about noon and 4:30 is when all of that material was deposited, which is pretty amazing. And we can see different layers in here that are more lithic rich or less lithic rich or more lithic rich. We can see beds that have been truncated, beds that are onlapping others. But again, the deposits are only providing us some record of what happened in the eruption, or some record of what happened in the pyroclastic density current, not the whole picture. So another way we might do this is by looking at numerical models. And this is some fantastic work that Joe Dufek has been doing for quite a few years now. And this is a very, very high spatial resolution numerical model, which combines, for those who care, it's an Eulerian Lagrangian model. So he's actually tracking some of the individual particles through the system, through space and time, as well as using a continuum approach. And using a model like this, you can see how a current develops these lobe and cleft instabilities. Those are entraining air. Those can get bigger and bigger. We can see great big billows that form along the back. And the beauty of a numerical model is once you have those results, you can slice them any way you want. You could take a slice like he's done here, where we're looking at a longitudinal slice down the length of the current. We could look at it along a plan view. We could cut this thing any way we want. But the challenge is that the numerical model might not have high enough resolution to see what we need. And we end up with a little bit by itself, a little bit of a chicken and egg problem, in that if we're using this model to study what's going on in the current, well, it would be nice to back our model up against something else. But if we don't have anything else to back it up with, then how do we know if our model is correct or not? And so some of the things that would be nice to know about are things like, what's the grain size in this eruption? What's the concentration? What's the temperature? What's the density doing? What's the velocity doing? Many of the same problems with the natural system still can arise in the numerical models, because we don't necessarily know how to back them out or how to validate them. So another way to study these then is with experiments, and that's clearly the subject of today's talk. The challenge here is that with experiments, you can only study some aspects of a pyroclastic density current, or that's honestly true for any set of experiments at all. If you want to study absolutely everything, the only way to study every aspect of a real volcanic eruption with experiments would be to make a full-scale volcanic eruption. And they don't let us do that, usually, ever. All right, so to do this is a cartoon schematic of the experimental facility that I used down in Suitland, Maryland. So if we imagine I really should have put a map because people here would know where it is. If we think about the diamond that is the District of Columbia, Suitland, Maryland is just over the southeast border of DC into Maryland. And Suitland Smithsonian has a great big facility where someone at lunch mentioned Raiders of the Lost Ark. So at the end of Raiders, where the Ark of the Covenant goes, that's Suitland, Maryland. It's, I think, in anthropology. So this is a schematic of the lab facility we have there. It's a chamber that's essentially intended to contain dust. So the chamber measures from the upstream to the downstream end about 8.5 meters. It's 6 meters wide and 2.5 meters tall. And within this, we can generate small particle-laden density currents. And we make these currents by loading talc, 20-micron talc particles onto a conveyor belt. We then feed the talc on that conveyor belt into the tank, and it falls down a chute. And then about 5 to 10% of the talc that falls down the chute comes out the bottom as a dilute cloud, a turbulent cloud of particles, and that is our model density current, or it is a density current. Now within here, we collect all sorts of different measurements. We have an array of temperature probes, which are indicated here by these little lines, and they are thousandth of an inch K-type thermocouples that are being logged at 3 hertz. We can actually go faster, but for our purposes, 3 hertz seems to work just fine. And these are small enough thermocouples that they're very fine gauge, so they respond quickly to changes in temperature. Their time constant is like about a 60th or a 100th of a second. They're small enough that they don't interfere with the flow, or they don't interfere substantially with the flow. So we can introduce a probe into the current, it doesn't change the current. We also illuminate the currents with a series of laser sheets. So in here we have a horizontal blue sheet, a vertical green sheet that's running down the length of the tank, and then a red sheet that's going in the horizontal plane, the vertical plane across the tank. And we use these 3 different colors of lasers because the cameras that we use can be, the sensors in the cameras are a CMOS sensor. So this is a picture of one of these CMOS sensors right here. This is the sensors that's in our iPhone. This is the sensor in most consumer cameras, in fact, many cameras, period. And the pixels here are grouped in little clusters of 4 with 2 green pixels, 1 blue, and 1 red. And the response of those pixels This is a fantastic and lucky development. The response of those pixels corresponds with our laser sheets. So a single camera looking into the tank can capture, in one instance, can capture an independent blue plane, green plane, and red plane. So we can see independently what our current is doing in different planes. And we could orient those laser sheets any way we might desire. Now, there's two other types of samples or sensors we can have in there. One, we'll see this a little bit, how this works a little bit later in the talk, is a rotating laser sheet that lets us get those 3D scans like was on the title slide. And lastly, we have a way to sample the deposits that are in the tank and generated by our currents. And you'll see later on that calling these devices sediment samplers is, well, it makes it sound much cooler than they are. All right, so experiments, the thing about experiments is they only work if they're properly scaled. And so in our case here, we're interested in studying dilute pyroclastic density currents. So a pyroclastic surge, or the fluffy part of a pyroclastic flow. And we pay attention to a series of dimensionless numbers. And the idea here is that if we can match the dimensionless numbers of our current to the dimensionless numbers of a real pyroclastic density current, then we have some hope that the dynamics that we see are similar to the dynamics of the natural system. So when we do this, we pay attention to some bulk parameters, such as the Reynolds number, which is essentially a measure of how turbulent, how turbulent is the current. We also pay attention to the Froude number. There's a pair of Richardson numbers, both a densimetric Richardson number and a thermal Richardson number. This energy number is essentially, think about it as another way of doing a thermal Richardson number. And then lastly, we have a couple of particle numbers, or turbulent numbers, that basically tell us how well our particles are coupled to the motions of the current. Now, when we look at our results, our numbers, and compare them with nature, we do really good for some things. Our Froude number is 1, and the natural experiment is 1. That's great. Our Richardson numbers, there's a range in the natural PDCs. Well, our experiments have a range that matches that. By changing the temperature of our currents, we can get the appropriate thermal Richardson number and the appropriate thermal to kinetic energy balance. And the Stokes number here, our currents have a very limited range of Stokes numbers, and their settling number is always less than 1. Now, natural currents have a huge range, but if we look at a natural dilute current, that range is very small and matches ours, and the same with the settling number. So we're doing really great with everything, except for the Reynolds number. And I have a feeling several of you know why we will never match that. And we can see why we can never get, yeah, Karen's nodding her head at that one. We'll never match the natural Reynolds number, and we know that if we look at the equation here. So the Reynolds number is the ratio of the density times the velocity times the thickness divided by the viscosity. In this case, it's the viscosity of air. Well, natural currents happen in air. Our currents happen in air. So both systems have the same denominator there, but our currents are about 100 times, well, 10 times less dense, 100 times slower, and 100 times smaller than a natural pyroclastic flow. So we'll never get that. And at some other time we can discuss if we could do it by changing the pressure or something. Turns out it's really hard to change the viscosity of a gas. Like we could depressurize the tank and we'll change the viscosity by a factor of 2, which is not very much. So that being said, our Reynolds numbers are way smaller than nature. However, we are fully turbulent, so we have reasonable confidence that we're capturing the large-scale dynamics of the system. All right, so what do these look like? We'll see a few videos here of the currents, and this is a view from the upstream end looking down. So this piece on the wall here is 28 feet away, and this is 20 feet wide. These little things here, these are sediment samplers, which if they look like 3x5 cards, it's because they are. We weigh them beforehand and weigh them afterwards, and that tells us how much deposit was laid there. And in a moment, we'll see a current come out, and this has been sped up by a factor of 5. So here we go. The current comes out. The green sheet is horizontal. We're seeing it spread more or less in all directions as it comes out. It looks like it's not over here, but that's just because the laser is not illuminating that part. This current spreads out, and it runs the length of the tank. And if we go back to the beginning of this guy, in a moment when we see it on the red sheet, you'll see what looks like sort of a classic density current profile here, where we have the head coming out like this. It looks kind of like we can see that it's spreading laterally, just like we'd expect in a cartoon version of a density current. The way my little scaling diagrams were drawn with a great big head and then a low body behind it. Now this changes if we look at a heated current. So this is essentially the same eruption rate, but this guy is warmer. And we see now when this comes out, it no longer spreads in all directions equally. Instead, it's pretty much sticking right down the middle. It's also lifting off and making this buoyant plume. In the blue sheet, you can see it rising up. In the red sheet, you see it quite dramatically. You see there's even some regions of backflow where the current, the leading edge is basically getting wicked back or pulled back in and entrained into the margins of this current as it comes out and lifts off. And if we were to look take another warm current, this is now a higher eruption rate, about 5 times as powerful of an eruption. We can see that this guy comes out and initially spreads a little bit more than our last current. But in a moment, we can see there is a plume starting to form. And as material lifts off into this plume, which you see especially close by the camera, everything you see gets pulled back towards the center line. And so we see that when we have these warm currents, we have a complex flow field. We have the runout distance. In this case, it still went quite a ways, but it's actually less far than a comparable cold or ambient temperature current. We see flow reversals, which is to say, if you're standing in one place and the flow goes over you this way, a minute later, it could actually get sucked back over you in the opposite direction, all from a single current. All right. So if we want to take those data and turn them into something a little more, I mean, those movies are fun, those movies are cool, but if we want to turn these into a more, something more quantitative, we can split the channels like I mentioned earlier, where we take our video images and we split them into independent red, green, and blue images, and then with a little bit of, essentially with a little bit of a calibration, we can reproject that stretched view. If I go back one slide. If we take, for instance, the green sheet, which at the moment is horizontal, if we take this view, that right there is a highly distorted image. But we can reproject that highly distorted green image into an orthogonal or dimensional image. And that's what we'll see here in a second. So first we'll look at a couple views from the side. We have to exit out. And this is a cold current coming in. We've changed the color scheme. It's really dark there. But this guy here comes across the bottom. We saw the head there. And we'll look at it one more time. So this cold current comes across. We have this motion of the head right here, a lot of entrainment happening right behind the head. It basically flows the length of the tank from left to right. Now if we look at, in contrast, a warm current with very similar eruption conditions, this guy comes out. It's again entraining, but rapidly lifting off, and just like we saw in those videos from a moment ago. Okay. And if we were to look at it, we could do the same thing now with the horizontal field of view. And let's see if I can do this right. So this is that cold current again that we saw just a moment ago. It comes in. It's going to spread out more or less uniformly across the room. Some of the craziness with the lighting here is just the lasers, variations in intensity. But it fills the tank, and in contrast, the hot guy spreads out and stays very, very focused. So the current really never makes it past about here. And when it lifts off, you can see it sucks back in right towards the center and ultimately lifts out of our field of view. Now if we take these different, if we were to take these observations, like for instance right here, and map the edge of the current, if we map where the edge of the current is, and we can change that through time, we could essentially see what is the inundation area of one of these currents through time. And we could then, so we get a time series of how far that's going. And our next slide shows that with, essentially this is showing us runout with time, or inundation with time. Now, the units here, we take that area that we would have measured enclosed by the loop, and we just take the square root so that the numbers are a little easier to understand. When we do this, we see, again, some systematic variations having to do with eruption rate and with temperature. So if we look at, in light blue here, this is a very low eruption rate current at 250, with a, don't pay attention to this too much, but at not a high temperature. This guy comes out and does not go nearly as far as these two ones in blue and black, which were an eruption rate of about 10 times higher, that flow out much further and much faster. If we crank the eruption rate up even more to this one here, which is also hotter, we see that it goes quite a bit further. When it lifts off, we see it actually pulls back in. So this is not an artifact of or spurious data, but there actually is. The current comes out, inundates a large area, and then sucks in, and for a little while has a limited area that it goes with. We see a similar pattern here in this red one, where again with the 350 current that goes out a little ways and then pulls back. Now, if we were to look at the deposits left behind by these, we could then also understand what record these are leaving. And some work that's still very much underway, we're trying to take the data that these deposit data we can get in the lab, to compare with natural systems, because ultimately, for most pyroclastic flows, deposits are all we have to go by. And this is just an example right here. It's a little hard to see, but there's, I think, 64 or 70 little black circles here indicating sediment samplers, so 3x5 cards. We can put a bunch of cards out. We can then measure the mass per unit area on them, and we can end up with basically contour maps of the deposits. And these end up providing us, these are very analogous to the isopack maps that volcanologists would make in the field. And we can use this to see again how deposit thickness, or mass in this case, varies as a function of distance, like we have right here. And I don't think I have it shown here, but if we were to plot a similar current, the data end up, which is wonderful, end up being highly reproducible. So that similar currents make very, very similar patterns. And we can see how these sedimentation patterns vary as a function of eruption patterns. So over here, this plot here shows us the eruption rate. And again, this is the farthest distance that we see a particular mass. So 10 to the minus 2.5 grams per centimeter squared. Someone else might be able to tell me what that exact number is. I think it's 3 milligrams per square centimeter, something like that. We see that very large or high eruption rate currents send material much farther than do low eruption rate currents, which maybe isn't too surprising. In fact, it's exactly what we'd expect, but it's heartening that our experiments show that. The other thing that we see is that if we look at the thermal Richardson number, which is a measure of essentially the temperature with hotter currents over here and colder currents over here, we see that as we make currents hotter, in this case there's a covariation with current size, but as we make them hotter, they actually end up going less far, which is again or covering a smaller area, which is what we see from looking at the videos. So it's nice that these different data sets are matching up. All right, so now we're going to start to shift gears a little bit and get into explaining why we see some of these differences in behavior and thinking about how density evolution might change. So I've mentioned earlier in the talk that these are density currents. They move because they're more dense than the atmosphere, but their density changes through time. So if their density changes, at a certain point, they stop moving laterally and they rise and lift off buoyantly as a plume. So that we really want to know what's going on with the density evolution. Now, if we look at the radial currents, the ambient temperature currents, we see that when these guys are erupted into the tank, they spread in more or less all directions equally. And these little black arrows here are supposed to be showing entrainment. It kind of looks like a frying pan, but it's supposed to be showing a current spreading in all directions equally. Now, in contrast, when we have a warm current come in, this guy might initially spread a little while radially, but the moment that any one part becomes less dense than the atmosphere, that parcel now lifts off buoyantly. Now, once it lifts off buoyantly, continuity will dictate that if it's rising up, other material has to get pulled in behind it. And so we see that a current might come in, and once it starts to lift off, its motion vertically prevents lateral expansion of the current. And we see in our videos, we can see there's also enhanced entrainment along the side. And we also know as these currents are lifting off, or as they rise up, they mix with material as they rise. So we can see that really entrainment and how these currents entrain and mix with air is telling us, or should be telling us, a lot about why these currents behave the way they do. All right, so to sum all that up, we know that the cold currents travel farther than the hot currents. The hot currents seem to lift off to form these plumes, which suggests, or not suggests, it shows us that they have a buoyancy reversal. And that buoyancy reversal then limits the lateral spreading. And finally, air entrainment is controlling that reversal. All right, so entrainment then is what we're going to spend most of the rest of the talk here talking about. And that's how do currents entrain air? Where do they entrain air? And how fast, or can we put a number on that? So the first part is, I guess we can use the sort of a dictionary definition, which would be that entrainment is turbulent mixing of ambient air into these currents. And it's a bulk quantity, which is to say we think about entrainment as happening over the entire current at once, but we know that it's happening due to local interactions. So essentially, if you sum all of the different mixing from all these half dozen turbulent eddies that we show here, that's what gives us the bulk number. Now, we can define entrainment as entrainment is the ratio of an entrainment velocity divided by the average current velocity, or the characteristic current velocity. Now, the entrainment velocity, there's a couple ways we'll go about doing it. One way is we can actually measure the vectors that are fluid coming into the current, which is a pretty wonderful way to do it if you have the data for it. The other way is to have the entrainment velocity be equal to the change in the current volume, so how much bigger is our current now, divided by the surface area of the current, divided by the amount of time that change happened. And if you play with the units, you do get units of meters per second squared there, or meters per second. So we do have, that is a velocity. And what's interesting is that if we look at most density currents, so a powder snow avalanche or a turbidity current or the cold pyroclastic density currents that we make in the lab, those have an entrainment of about 0.1 to 0.2 pretty much always. That's what their entrainment is. And as we'll show you in a few more slides, that's not the value we get when we have hot currents. All right. So one other way here where we know that entrainment is happening, and these data will come into play a little bit later, is that we can see that these currents' temperatures are changing. And the reason they're changing is these hot currents are mixing in cold air, which has the effect of cooling the current. So if we look at this, we'll see a series of a whole lot of squiggly lines in this plot here in a second. We've shifted up the temperature so that this right here would actually be 0. So the thing to pay attention here is what's the relative offset between this position and the peak values of a given position. So when we look in this case at, this is a warm current that comes in at the 1 meter thermocouples, we see that the difference between the initial temperature and the peak value is about, I think that's about 4 or 4.5 degrees C. If we look at this current a half meter later, it's now that difference is about 4 degrees C, or 3.5 degrees C. And if we shift, as we look down further and further, we see that the difference in temperature becomes ever smaller, which is exactly what you'd expect. And fortunately, when you get to where the current never made it, you don't see anything, which is also encouraging. So we can see that the temperature is recording the entrainment. Now, if we think about what parts of the current are entraining air, well, our little cartoon would suggest that it's turbulent eddies along the margin of the current. We're getting things mixing in along the sides. Now, if we take our two-dimensional movie views, our slices, we can measure the velocity field. So we can take one of these images, we can get rid of the background, and so this picture on the right is a zoomed-in view of about this area here. And we can then, using feature tracking velocity, we can do the cross correlation of one image to the next, to the next, to the next, and we can get a velocity series such as here, where again, we're now looking at this zoomed in region in the magenta box on the left, and we can see that there's a little vector field going everywhere. And as we were mentioning earlier, some of the vectors in here, some of the individual arrows might be spurious, but in general, the patterns that we see, and we can track them through time, clearly show turbulent structures within the currents. Now, if we look along the margins of the current, such as this guy here, so I mentioned a spurious one, this guy here is probably not real, almost certainly not real. But when we see, like in here, where there's a whole family of vectors all flowing inward, that's a good sign that actually is a real spot. So if we look at along the margins of our current and look inward and find within some area of interest, indicated by these little cone shapes, if we find what's the component of velocity that's directed normal to our surface here, that gives us a measure of how much material is being mixed in or entrained by these currents. So it gives us essentially a map of what is the entrainment velocity along the margins of the current. And we see that right here. If we take that, we can see that there's regions, I guess, where this yellow star is. There's a region of very high entrainment. You go a little bit further down, you have some regions that are actively expanding. So a negative entrainment would mean that rather than material coming into the current, the side of the current is actually pushing outward. And we can do this around the whole margins of the current, and you get a sort of chaotic diagram like this. But what's interesting about this, so the current was moving in that direction, is we see regions, alternating regions of vigorous entrainment, like right here, with vigorous expansion right there, and then entrainment. So this is like the lobe and cleft structures that we saw on that numerical model picture at the beginning, where we know that entrainment is happening along the leading edges of these currents. We also see large regions along the sides that have positive entrainment. So this is a big region right here where air is being sucked in along the margins of the current. Now, if we want to see what the entrainment series is for a whole current through time, we can just take and sum up all of the positive values. Yes, sir?
Yeah, I just want to make sure I fully understand this process.
Yep.
So it's a type of gulping.
So yeah, think of it as it's it's basically gulping. So the simple way would be if you have sort of like a billow that's coming along the side, it's gulping, or you have at the front edge, you have I need bigger hands. You have like a lobe and cleft instability where its parts are able to actually engulfing air as it comes along at the front, or along the back of the head where we often see it. The current's going this way, you have this great big roller right there that's ingesting air in and sucking it very nicely into the body.
But the flow itself is never really just inhaling in terms of a Bernoulli type effect?
There a little bit, but it's
Okay.
not too
That's not really the major thing.
I think it's largely an engulfing kind of a thing. Yep.
Thanks.
So if we then take a time series, we could take our current, we could sum up the positive values around this, and then come up with some characteristic measure of what is the entrainment coming in, and we could get an entrainment velocity, but ultimately we could divide that by the current velocity and get a plot like this, where we're seeing that in this case here, this is a warm current. It came out, it had an initial rise in entrainment to about 0.25 or something, followed by a decrease, and then eventually it was stable here around 0.1 or something, and a bit later this guy actually started to increase again. And that's probably where this current was now lifting off and pulling itself all together. Now if we look at the detail of the first 10 seconds or so of that plot, we can see there's sort of a quasi-periodic or episodic changes in entrainment, which are essentially recording the passage of large-scale eddies in the system. So this again gets that entrainment, properly speaking, it's a bulk parameter for the whole current, but it's the sum of lots of little tiny localized processes. Okay, so the other way we can measure entrainment is with the disco laser. So I told folks at lunch that we have the stationary lasers. We also have, and do not tell the safety people about this, but we have a laser sheet that we shoot at a mirror, and then we spin the mirror at really high speed. So don't look at the mirror, it will hurt you. But the idea with this is that if we have the current, if imagine this were to stop rotating right there, we have a current flowing across the room like this. Now, as this current moves, if we have a laser sheet that shoots that current and sweeps through it, if the sheet moves faster than the current, and it moves substantially faster than the current, then we can treat a whole series of images as being all from one time. And we can essentially treat them as being motionless. And we collect images, so we have a laser sheet then that's sweeping through the current at about 10 hertz, and we have a high-speed camera that's imaging that laser sheet at 1,000 frames per second. Now if we take, with a little bit of trigonometry, we can convert this sort of fan-shaped array of images into, each image has pixel coordinates ij, but we can convert those pixel coordinates into real-world x, y, z positions, and we can ultimately end up with this nice three-dimensional reconstruction of a current. And we can do this essentially as much memory as the high-speed camera has. So 30 or 40 reconstructions for a given current, and we can collect these at about, we could collect them at 10 times a second, but that wouldn't give us much. So instead we collect them at about 2 times a second. Now the results that come out the other end, here's a couple ones right here. The bottom, this is that current from the title slide. The thing doesn't really have a shark fin. This is just an artifact of, I think, a thermocouple. But you can see that this looks kind of like a real powder snow avalanche or a real turbidity current flowing across the room. And up above we have a current that had just ended and now is lifting off and has formed a buoyant plume that's rising up. Now what these allow us to do, in addition to get some groovy looking movies, is they let us actually get the volume and the surface area. So because these reconstructions are the voxel size is 1 centimeter, if I want to know what the volume of my current is, I just ask MATLAB to count all the 1 values and disregard everything else. If I want to know the surface area, I can just say, well, what pixels are on the interface between the current and the not current? And so when we do this, we get something like this, where for this particular experiment at 10.7 seconds, it has a volume that is not significant. It has a volume of about 2 cubic meters, a surface area of, would that be a half a square meter, if I'm doing my math right? No, 4.6 square meters is the surface area. And we're ultimately interested in what is the entrainment of this current. Well, entrainment is equal to the entrainment velocity divided by the current velocity. The current velocity is easy. We just measure where is the nose of the current at time 1, where is it at time 2, that gives us a velocity. The entrainment velocity, you'll remember, is the change in volume divided by area times time. Well, we have area, we have volume, and we have time. So we can calculate all this. So if we think about this then, the volume at our new time is the old volume. Sorry. We can measure the new volume, and we can measure the old volume. We know how fast we're introducing new current into the system. With our temperature data, we can calculate how much of a change in volume is because we've ingested material versus how much is because we're expanding old material. And lastly, that then gives us the thing that we actually want, which is the entrainment. So we rearrange all those, and we can get our entrainment volume and therefore our entrainment velocity. And then we can get a somewhat noisy looking time series like this, where we have some places where the laser goes haywire in one direction and then the other direction, but we have a clear track here showing the behavior of the current, how fast it's entraining or how much volume it's entrained through time. And we can then also look at the entrainment velocity, which is again or the entrainment, there we go. So we can see that this is a current where there's a little bit of spotty things at the beginning, but for a while this guy was entraining at about 0.5 to up to, in some instances, maybe 1. And then it looks like it might have been decreasing through time. Now, clearly, there's a negative entrainment doesn't make sense. This would be, I guess, like the current collapsing, like a neutron star or something, and getting smaller. That probably is not happening. But the basic pattern here of an entrainment around 0.5 and then a decrease through time is valid. And we can think about this then ultimately. So these experiments are a lot of fun. They make cool videos. But ultimately, we would like to be able to relate our experiments to nature. And so the first thing we did was to take, or one of the things we've done is to take our data, and so just to make sure that our data don't show some bias, these entrainment values don't show some bias with the eruption rate or the mass flux. So what's nice here is that if we look at our data, there's no trend that says, you know, at a high mass flux, okay, 10 grams per second probably isn't very high, but I think that's high. Sorry, a little bit of a joke there. A real volcanic eruption might be 10 to the 8th kilograms per second, so we're 11 orders of magnitude smaller. If we want to take our results and have them have any applicability to something 11 orders of magnitude larger, it would be nice if we don't see some trend in entrainment. And we don't. If we look at these heated currents, they all have kind of a similar range up there. These cold guys have a similar range down here. And now if we look at them with respect to a thermal parameter, like the thermal Richardson number, which again, hot currents out here, cold currents down here, we see that our cold currents basically give the same answer that we'd expect from a powder snow avalanche or a turbidity current, which is good. Those should be very, very similar. But if we take our warm currents, as we make things warmer and warmer, we actually get increasing entrainment, which is maybe not surprising given what we see in our movies, but it's encouraging that we see that result. All right. So this also suggests then that we should be able to, if we know the thermal Richardson number of a natural current, we should be able to infer its entrainment. Or flipping it the other way, if we have observations of natural currents and we can watch how they entrain air, we might be able to use that to understand the thermal Richardson number, which would give us an idea of their density and their temperature structure. All right, so last couple things here. We can then take some of these also into some predictive models. And so sometimes people ask me, do we model a specific volcano? And the answer is no. And I would also say that any hazard map that I were to produce, you should do not use it. If I am studying the volcano, you should probably go somewhere else because don't rely on my predictions. But that being said, we can take some of the results here and put them into a very, very simple numerical model, just a box model, and understand or see what the effects of entrainment are on pyroclastic flow runout. So if we apply our classical numbers of about 0.1 or 0.15 to entrainment, we see that we predict, in this case here, a current that was running, an eruption being fed for about 45 minutes, could, all else being equal, might make a current that's going out to 20 kilometers. That's a long ways away. On the other hand, if we increase the entrainment to 0.2, it's only going about 12 kilometers, and if it's, 12 kilometers, and if we increase this entrainment to 0.3, we can see this current goes much, much, much less far. So we can see, even with a simple model here, or a very simple, almost just arithmetic, we can see that the effect of entrainment on runout is substantial. So we really need to have a better understanding of runout of these natural currents. We can also see that based on how much air they entrain, that'll control how hot they are, which has an effect then for how hot is the material that they're depositing. So to try and wrap this all up then, hopefully what I've left today is that we can see that the basic behavior of pyroclastic density currents, that is to say how far they go and do they lift off, when they lift off, that's controlled by the eruption rate and the temperature. We can see that their thermal effects, or the controls on whether a current spreads radially or is pulled in laterally, is really related to the entrainment, and that the thermal effects of entrainment control that behavior. We see that the entrainment occurs through the margins of the current at the head, and also along the lateral margins, the back of the head, and also at the lobe and cleft instabilities at the front, and we can put numbers on those. And finally, the bulk entrainment, we think we can predict that based on the thermal Richardson number. So with that, those two little take-home messages, I'll be done. Thank you very much.
So sort of the big idea for natural hazards here is so the hotter currents travel less far than the cold currents. But if you entrain more air, won't it cool fairly quickly and be less destructive?
Well, so as you entrain air, though, then you're converting that thermal energy basically becomes, like a better term, think of it as buoyancy, or it is buoyancy. So now instead of going, you have a hot current, it goes out fast and entrains air, now it lifts off. And so it'll go less far on the ground, but now you might be making a larger plume from a hazard standpoint. This is now a bigger plume that goes up and shoots down the airplanes. So there's some, there's no, if the pyroclastic flow is happening, there's no good scenario. Yeah.
Can you, from these experiments, can you back calculate what the temperatures would have to be for these different scenarios that you just gave up with entrainments of like 0.1 or 0.3?
Yep, yeah, that's right. So the hard part there would be we have to have some good idea of what the density and the thickness of the natural current is. But then with those parameters, absolutely, we can start to say, well, there it sort of ends up being that you'd have a family of solutions. So if the critical Richardson number is, if you need to have a Richardson number of 0.4, then we could say, well, if your current is this thick, it needs this density and this temperature, or it would be somewhere along this curve in density and thickness.
So the follow-up to that is, are we very good at all at predicting what the temperature of a pyroclastic flow is going to be?
Am I?
No,
are
other
we?
people.
Or are we? So
anybody.
I think depending on the system, yeah, actually we have a reasonable chance, and it ends up being very quickly a very ugly nonlinear problem. But we know that the current cannot be hotter than the magma that it's erupting from, and we know, so if it's a lava dome, if it's Cinnabung lava dome, then we can look at the rocks and get a temperature estimate based on thermal barometry, or point a IR camera and get a minimum estimate of the temperature, and that would give us something that we know that's the hottest it could be. And then we know that currents like that are, let's see, depending on the eruption mechanism, we have sort of a different prediction for how hot it should evolve through time, and whether it'll stay in that hotter range or that colder range. I don't know if that's a good answer.
Yeah, that's fine.
Yeah. Yes, sir.
I got a few experimental questions.
Yeah.
First of all, how do you heat this stuff?
Oh, that's so we
And
heat
how
it
hot do you heat it?
Yes, so we heat them in a toaster oven. It's a laboratory furnace. It's a toaster oven, Black & Decker. We heat that up to, at a certain temperature, basically it'll, like the current said 250 or 350 C. We'll heat them to a certain temperature for 30 minutes or an hour. In a given run, we'll try and always keep that a very controlled, constant time. And then when we load them onto the belt, they're still essentially that temperature. When they come into the chute or come out the bottom of the chute, they've already interacted with air and are much, much cooler. So the currents as they come out are about, if we heat it up to 250 in the oven, when it comes out, it's maybe the room temperature plus 8 or plus 10. So which is actually pretty amazing that we have, our currents are, in all, I guess I skipped over this. In almost all respects, our currents are 100 times colder, slower, and less thick or smaller than the natural currents.
Follow-up, can you use other materials other than talc?
Yep, so
Different coarseness, grain size,
Sure.
mesh?
Yep,
different
so
sensors?
we absolutely can use other materials. We use talc for a couple reasons. One, it's cheap and it's very affordable and we can buy it with a very known size distribution. So we want to try and limit the unknowns in our system. So its size distribution is 20 microns plus or minus about 2 or 3, whereas other things might not be as well characterized. We can use other grain sizes, and it turns out that the talc ends up illuminating nicely, so it shows up better for the detectors, and also stays airborne a little bit nicer than some of the coarser stuff, which is not surprising. It also doesn't clump. Like 3 micron talc ends up behaving as more like 100 micron talc because it electrostatically all clumps together, and suddenly it's not 3 microns, it's big chunky things. The other reason we use talc is that it is less hard than the plexiglass windows. So it's a hardness of 1. It doesn't scratch anything, whereas pretty much anything else will scratch plexiglass.
And do you ever mix coarser stuff in with the finer to more closely mimic a real life situation?
So on these experiments, we haven't ever, and that's just more been because of time and trying to limit our variables. We certainly can. The idea, and we've thought specifically about that with the notion that so we have those little sediment cards sampling the sediment on the floor. But if you had a stack of a series of cards at different heights, and a particle mixture coming out, you could see how a current is partitioning into coarser and finer segments, or not partitioning, which would also be interesting. Yeah.
What's the role of, or is there any role of viscous dissipation in heating the current?
So for these ones, these are low enough energy that there shouldn't really be any viscous dissipation. And even in the natural currents, they are big enough and energetic enough that viscous dissipation shouldn't be happening. Now that's not true in the magma right before fragmentation. There's almost certainly a lot of viscous dissipation happening, but for these turbulent ones, it shouldn't really be an issue. Yeah.
Just to follow up, the shape of the particles is irrelevant because talc is so plated.
That's right. So ours, we've imaged it with, we calculate them as a sphere. But you're right, it is palladium. When we've looked at it with the SEM, that they're like little blocky things that are, I don't know, aspect ratio. If it was a plate this big, then it would have a thickness of about that. So I guess that's a 2-to-1 aspect ratio. So for our purposes there, and at the range in the thing about the settling velocities and the the fall velocities of these, we think it's reasonable as a first pass to treat them as a sphere. Now, if we were to look at particle interactions or other things, then we might have to think about particle shapes.
Yeah, so I have no direct experience, fortunately, but in many places I read about pyroclastic current being channelized in a valley or something like this, and I'm just wondering how that would affect, the entrainment on the side or the distance that we go to, or if maybe the hot ones are being less sensitive to those aspects, etc. I'm trying to think about.
No, that's great.
volcanoes.
So if you were to send one of these, and we've been meaning, I think I was telling Ved this, we've been wanting to run these experiments, just haven't gotten around to it, but to run them down a channelized thing, essentially a valley with plateaus on either side, not just down a true channel. And having run experiments down a true channel where they couldn't expand at all laterally, I know that those ones go a long ways compared with these ones right here. And so if you were to send it down essentially a river valley, that should increase the runout distance and essentially limit entrainment in from the sides. And so it should keep them hotter and focus them and get them a lot further. One of the things that we've been looking to do or hoping to do is to have one where it would come down a river valley. I don't have to walk there. Come down a river valley with a bend, because natural PFs do that, and often that's where a natural PF, the denser part makes the turn, but the fluffy part doesn't make the turn, and that's when you get a pyroclastic surge that might, well, unfortunately, that's one of the big hazards, is that that's where the village happens to be, and they get destroyed by a pyroclastic surge.
Really quick on that, you may have mentioned that when you calculate entrainment, was that throughout the entire density current or just ahead?
Around the whole way around everywhere around the margins, both in the plan view, so both in the horizontal sheet and also in the vertical plane. So that one of the challenges is that the 3D observations tell us what the bulk entrainment is, but don't tell us where it's happening. Whereas the 2D ones give us a beautiful 2 slices that tell us very good detail where it's happening in that slice. But if there's a slice right here, I don't know how representative that is of something 5 centimeters above it, or the same with the vertical slice. If it's something 10 centimeters either side, might be very different.
Do you think the entrainment will be very different along the distance?
Maybe. Certainly over time, I think that early on the head dominates the signal, and the head is very, very efficient at entraining air. As the head becomes volumetrically smaller compared with the rest of the current, or a smaller volume fraction, it becomes less dominant, and then at that point, for a hot current, the sides should really dominate. Right. Yeah.
James.
My question may be completely off base, but I'll just explain what I think I understood. The entrainment as the thing goes out is because it's being pushed out and it rotates up. And then so you get entrainment as this thing moves out, and then it rises because of the entrainment and the heat. I didn't catch, does the amount of entrainment change for a flow as you go from the bottom part up? Like, does it just stop when it's going? I mean,
as it's lifting off, is it still entraining?
Yeah.
So yeah, so as it lifts off, that plume is also now able to entrain air,
Right.
and
Does it change the amount of it?
and the plumes can be plumes actually entrain at 0.2, I think, is there, or 0.13. So I forget. Plumes end up being very, very.
So more.
Yeah, well, it depends on where. To get to your first part, the entrainment as the current comes out. So this guy here is going in this direction. There's entrainment happening along these sort of lobe and cleft structures at the front, where it's engulfing air.
Yeah.
It's coming out and engulfing it. But then there's a big roller kind of a vortex that gets set up here, and that guy is very good at pulling air in on the back side there.
Is that because it's being pushed from the bottom?
Yeah, the bottom is going to be moving a little bit faster than the top. The top is having drag with the air. So as it comes out, a current, if there was no.
Why does it drag on the bottom?
It does have drag against the floor, but the drag, it ends up, if we're looking at the velocity profile, it would have a 0 velocity bottom, then a higher velocity nose, and then the top slows down again. So it's, I don't know if that helps. But then it is also entraining along the sides through, this is not a good picture for it, but basically any place where you have shear between the higher velocity current and slower velocity air, that's going to set up these eddies, which ultimately pull some of that air in.
Completely different question from last time. So eventually with those 3D images here, we're almost back to the natural case where we see the outside.
We see the outside,
but do you see the interior with your disco laser?
We do, and if I had a brighter laser, you should be able, you can see structure with that. So just like with the normal slices, you can see the structures. With the moving laser, you could also see structure, so you should be able to then get the true 3D structure. The challenge is that you need, my high-speed camera is very nice, but I either need a better, higher speed camera, or something that's better, more sensitive to the light, or I need brighter and brighter lasers. And at this point, there's like anywhere from 4 to 6 lasers that are all ganged together trying to make a sheet, and it works. But that is one of the goals, would be to try and actually get the true 3D structure, so you're not just seeing the exterior, but you're seeing the interior. Now, one difference though with these systems as opposed to nature is that I can run the same experiment with the normal laser slices and then with this and they're reasonably reproducible, so I can get some idea of what's going on. I can also have temperature sensors in here, so I can get that information, which we, of course, can't get in the natural currents.
Does the experiments change if you change the slope on which these currents are coming to?
It should. We've never yet changed the slope. There are many, and that's what we've been wanting to do, but there's too many parameters to change, basically. So we try and limit our parameter space.
How many experiments go into a study like this, and then how much preparation goes into, do you have to sweep out the chamber every time?
Yeah, so that is, yes, you're on the right track. So the rate limiting step is, there's two things to be rate limiting. Normally the rate limiting step is cleaning the tank. So for the 2D, where we have the stationary lasers, we want the floor and the walls to be black. So, and they're painted black, but after you dump a bunch of white talc in there, they're not black anymore. So who would have guessed? So we sweep the floor, we vacuum the floor, then we mop the floor. And depending on how good I am and how tired I am, it's either really good or you start to see swirls. And then that takes, when I'm doing those, I can run maybe an experiment an hour in sort of a sustainable fashion. With the disco laser ones, you can actually run those a bit more. The rate limiting step there, you don't have to get the floor quite as clean, but you have to wait for the data to transfer from the camera to the computer, which, depending on how many images you take, might be like an hour or an hour and a half of just, it's like watching the paint dry, watching a little status bar say that you've downloaded 20,000 out of 20,500 images. So
this is, that image right there is one experiment.
This is
Or not an average of a bunch.
No, this is there's like 200 images. Make this up. This is at, I think, 10.7 seconds or something. This is from one experiment, but there'd be 30 other reconstructions just like this from this experiment, so you'd see it going out. And then the other part that's hard is then actually crunching all the data. So what's amazing to me is that the data processing for this is actually really fast. Like, I can get back from the lab, tell MATLAB to process this, and an hour later it's done the entire experiment, which is great. Doing the velocity fields and all that for a single experiment might take like 30 hours or 20 hours of computer time as it crunches through. So.
Okay, so this is really getting technical. But you showed us one way that you are estimating the amount of entrainment by looking at that velocity.
Yeah, sort of the normal component. Yeah.
Have you tried like computing the divergence of the flow field or something like that?
Yep, we can look at that, and the hard part there is that I don't. So yes, we can look at the divergence of the flow field, and we can see where things are converging or diverging. But the hard part is, I don't know if they're going then up or down.
Oh, because you have two.
Yeah, because it's not. So like I've done a similar thing with where I was looking at velocities on the surface of water, and I knew then if it can't go up. So if they're coming together, it must be going down, or if they're going apart, it must be coming up right there. So in that case, I was able to constrain it. In this one, I would just know if it's coming, I guess, normal to the field of view, but I wouldn't know if it's up or down. But that is a good idea, because it should show us something what's going on.
One last question. Any applicability to studying landslides? Can your apparatus do landslides?
Probably not. We're set up to do.
If Mon
dust
gave you a lot of money to
well, how much money? And can I buy a plane ticket? And no. So this is essentially, it's a great room for doing dust in air, particle experiments in air. For something that's a higher energy system like a landslide, this setup wouldn't do it. Now inside that room, we could probably set up something, a slope to look at something going down it, but it would be more just to use that room because it's a big room than to use the the big box.
There is an experimental facility
Yeah.
to do landslides.
That's right. Yeah, as Karen saying, there's
Go to Dick Iverson's.
in Oregon it's like a 100-meter long chute that goes down the side of a mountain, and they have basically a dump truck sit at the top, dump everything out, and watch what happens. So it's really cool.
It is really cool.
Yeah. Yeah. Thank you.